Hello, my name is Alex Mathewson. Throughout this presentation, I will provide you with an interpretation of the mathematics and numeracy used in the Australian Army Aviation Corps. I will provide you with a range of mathematical problems that could be presented as an inspiration for the beginning of a mathematics or STEM unit. Within the Australian Army Aviation Corps, there are a range of roles that can be adopted. Whether they are flying, maintaining, or in a support role, they will work closely with an impressive fleet of helicopters. These helicopters include Black Hawks, Chinooks, ARH Tigers, and the MRH-90. When I first started thinking about what mathematics might be involved in Army aviation, questions came to my mind such as, what would employees face when working with helicopters on a daily basis? They would have to use their mathematical knowledge to solve problems involving speed and distance. Alongside this knowledge of speed and distance, it would be essential to find out how much fuel is needed for this task. The weight distribution of passengers in the helicopter would entail thinking to ensure the helicopter flies in a straight line and stays upright. But how do we know how these problems can be solved? Well, I was lucky enough to interview the head of the Royal Australian Electrical and Mechanical Engineering Corps, Major General Andrew Mathewson. Andrew Mathewson grew up on a vineyard in Mildura before joining the Army as an apprentice fitter and turner in the 1980s at age 15. He entered the Royal Military College in 1986, graduating into the Royal Australian Electrical and Mechanical Engineers in mid-1987. Early postings were predominantly technical. After completing his bachelor's in mechanical engineering, Andrew completed his master's in science, business and administration, and defence studies. Andrew is currently the head of helicopters and tactical unmanned aerial systems in defence. In the beginning of Andrew's engineering career, he initially completed his Bachelor's of Mechanical Engineering. Here, the core of his mathematical competencies within aviation were formed. Due to Andrew graduating from university over 20 years ago, I've conducted some more current, extensive research on the required mathematical knowledge in order to study the same degree that Andrew completed to get where he is today. Mechanical engineers design, manufacture, and optimize specialist machines and processes. As part of their Bachelor of Mechanical Engineering study, they learn how to solve important problems. The core courses of mechanical engineering teach them to develop situations using robotics, new advanced materials, the fundamental laws of energy and generation and transmission, and the computer control of physical systems. The degree could lead to the work on everything from power plants to air conditioners, aircraft engines, and race cars. Although mathematics is incorporated into most of engineering subjects, engineers at the Australian National University are required to undertake only 2 math-centred units, Mathematics and Applications 1 and 2. Here the learning outcomes are to explain the fundamental concepts of calculus and linear algebra and their role in modern mathematics and applied contexts, demonstrate accurate and efficient use of calculus and linear algebra techniques, demonstrate capacity for mathematical reasoning through explaining concepts from calculus and linear algebra, applying problem solving using calculus and linear algebra techniques applied to diverse situations in physics, engineering, and other mathematical contexts. I asked Andrew about the key mathematical concepts incorporated in Army aviation. He said that a lot of mathematics is used in engineering calculations, particularly in relation to stress and fatigue on individual components in the aircraft. A more practical example of this use of mathematics is the work done to double check the aircraft computer calculation on fuel usage. So everyone needs to understand the mathematical relationships and to complete calculations rather than to just rely on the computer with no understanding of the context or risk. For example, they use algebraic algorithms to determine the influence of external factors such as wind speed, altitude, and load on fuel usage. They use geometric analysis to determine sling loads in all instances. Estimation remains important to check the calculation results are close to what they expect. Andrew mentioned that a common calculation that is implemented while working with helicopters is working out how much fuel is required for helicopters to travel from one location to another. This calculation then changes if a slung load is required. I asked Andrew about the utility of this equation and how it has changed over time with technology. He said that fuel use equations are normally done by computers on the helicopter, but it is still extremely relevant to understand the mathematics just to double check the machine. The equation displayed on this slide was provided to me by Andrew to demonstrate this common calculation implemented while working with fuel and helicopters. I will draw more closely on this equation later. Now it's time that we apply this knowledge that we've learnt from Andrew and research into an educational setting. How can we use this in a classroom as a tool for learning? STEM, being science, technology, engineering and mathematics education, is an umbrella of the Australian curriculum learning areas of science, technology and mathematics. This discussion about Army aviation provides your class with a range of opportunities to use these curriculum subject areas, leading to open-ended student-initiated tasks that incorporate technology, science, engineering, and mathematics. Now, back to the equation that I mentioned before, which Andrew kindly provided us with. As educators, we need to explain the mathematical relationships that exist in everyday workplaces. Therefore, rather than presenting the students with a formula for them just to insert the data, it is far more important to understand the relationship between each of the factors. As a practical example, here the pilot needs to be comfortable that he has enough fuel to complete their mission. The fuel consumption rate will vary depending on the flight conditions, like headwind and the load carried by the aircraft. By multiplying the fuel consumption by the planned distance, the pilot can calculate the fuel needed. Of course, some spare fuel will always need to be available for taxiing and any delays where the helicopter might need to hover. Now, before presenting the problems, as a whole class, an inquiry-based discussion should take place to understand the mathematics and technology surrounding aviation. You should discuss why fuel is required for helicopters, discuss how the rate of fuel being consumed is calculated to begin with, and how you can work out the distance between one location and another. So this problem here provides a simple equation to find out the fuel needed in order for the helicopter to travel from one location to another. Students should be encouraged to draw a diagram to ensure they fully understand what the question is asking them to find out, as well as using estimation throughout to make sure the answer makes sense. So to demonstrate their understandings, the students should solve the problems using steps similar to the following ones. So the first step to all problem solving should be drawing a diagram of what the problem is asking. They should then move the units from the problem into the provided formula in order to find out what piece of information is missing. The student should then realize that in order to find out how much fuel is required, they need to multiply the fuel usage, which is the 1.5 litres per kilometre, by the distance they are travelling, which is 320 kilometres. When multiplying with decimals, it is often important to estimate what the final answer will be to ensure that when you get that final answer, that answer has all of the place values in the correct spot. Now, we know that the answer will be more than 1 times 320, which is 320, and less than 2 times 320, which is 640. So the answer should lie somewhere in between 320 and 640 kilometres. The student should then work out what 320 multiplied by 1.5 is. The final answer should be that the helicopter, the Black Hawk, will need 480 litres of fuel to travel from Sydney to Canberra. Now, once this understanding is demonstrated by all of the students, you could then introduce a variable into the situation by making a different and possibly slightly more challenging problem for them.